Now switching to English to start the second lecture of our course. Today I want to focus more on qubits. So that's the system that we're basically using the entire class. I will start with a review and going deep into some things that I didn't have the time to talk about last class. I mentioned, but I didn't go that deep. And especially for the qubit system. And then we will talk about one application for quantum cryptography. So we're going directly to this very practical application that uses the system of one qubit. Later, next week, we're going to move to high dimensional systems, and especially more than one qubit. But today, we're still going to focus on one qubit. Okay. Just a minute. Just a minute, I'm having some technical issues here. Okay, I'm back. Okay, so the references for today, there is this book by my former advisor. He was my all life advisor, scientific initiation, master's, and PhD. It's on the Moodle. It will be on the Moodle eventually. Nielsen and Schwang, they talk about cryptography on chapter 12. And the things that I'm going to say are basically on section 12.6, but the introduction of chapter 12 is also important. And I also am going to share with you the original BB84 paper. BB84 is the name of a protocol that you understand later why. This is a very beautiful and simple paper, and it's one of the most important papers and most important results in the history of the field. So it is, and it's a good paper to read. So it's not good to read, not just because of its importance, but it's also nice reading it. And also some notes on another cryptography protocol that's called bit commitment. I'll share this with you later. Okay, so today we focus on the qubit, which is a two-dimensional system. We will use these symbols for the basis let me for the basis, the canonical basis. Why is it doing this really weird thing? For some reason, I'm having it like writing up dashed. I have no idea why. I have to find out why it's doing that. I guess it's working. So this is going to be the canonical basis for us. And in principle, alpha and beta could be any complex number as long as they satisfy the normalization condition. That comes from the probabilistic interpretation of these state vectors. Okay. But last class, we saw that there is equivalence relation between vectors. So there is more than one vector that represents the same state. There is an infinite number of vectors that represent the same state. And the relation between them is this, what we call a global phase. So a global phase is irrelevant with respect to the state that that vector represents. So we can use this equivalence, this redundancy, to simplify our representation of a state of a qubit. And what we do is to, inside this infinite class of vectors that represent the same state, we choose only one representative. And with this, we made this calculation in last class. We arrived at this condition here. So with only these two real parameters, I can represent all the states of a qubit. Not all unit vectors. There are unit vectors in C2 that are not here, but every class of vectors that represents a state, there is one such vector like this inside that class. So with that, we represent all states, not all vectors, but all states. So this these parameters are real. We could interpret it as an angle, as we are going to do in a moment. Phi has to run from 0 to 2 pi. And theta runs from 0 to pi. Okay. The reason why we divide it by 2 is just so we get a more nice geometrical picture of this in the end. So it's a choice just to make it look beautiful in the end. Okay. So now we are going to interpret these two parameters, theta and phi, as coordinates in a spherical I forgot the name in English, and I also forgot the name in Portuguese, but we are going to use spherical coordinates to represent these things with the angle parameters of the coordinates as these theta and phi. So what we are going to do when we have spherical coordinates, we have three parameters, are theta and phi. Here it's the opposite. Okay, it doesn't matter. I don't remember the order. I will use one here and I'll do the calculations later. I'll probably have to change it because I will choose it wrong right now. So we will see. So in spherical coordinates, we have x equal to r cosinus of phi cosinus of theta. I'm not sure if this is correct. Okay. So perhaps I'll have to change the role of theta and phi. We're going to do some calculations in a minute, and then we're gonna figure out if I chose this correctly. Y is our sinus of phi, cosinus of theta, and Z is equal to R sinus of theta. And here we're going to choose R equal to 1. So we're going to use just the
I think
Pascal.
I think the cosine and sine of theta are you flipped.
Yes,
I think
yes,
it should
yes, yes,
be
yes,
sine
yes,
in
yes,
x and
yes,
y.
yes, 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 totally correct. Thank you. And we are just going to use the outside, the casca of the sphere, okay? And then this is going to have a one-to-one relation. These points will have a one-to-one relation with that set of vectors psi that I have here, which is going to give us a one-to-one relation between states and points on the sphere. So we have a one-to-one relation between points in the sphere and qubit states. Okay. So let's see the representation of a few important states. And in particular, I'm going to look at 0, 1, plus, and minus, remembering that plus is 1 over square root of 2. Zero plus 1, and minus is 1 over square root of 2, 0 minus 1. Okay, so now we need to understand what is the angles theta and phi for all of these four vectors. So remembering that we have psi equal to cosinus of theta over 2, 0, plus e alpha, e to the e alpha, sinus of theta over 2, 1. So for 0, we need cosinus of theta over 2 to be equal to 1, e to the phi theta over 2 to be equal to 0. So here the alpha is not going to make any difference because we need to choose this to be equal to 0. And hence theta theta needs to be 0. Alpha could be anything, but that's not going to change the point in the spherical coordinates. So if we have cosinus of phi, and phi could be anything. Phi could be anything, yeah. Here is phi, it's not alpha. Phi could be anything. So this is cosinus of phi of theta. Let me just get what I wrote before to see if it's going to hold. So R is equal to 1, so I can eliminate this already. If this is like this, theta is equal to 0, so this is equal to 1, and both of these are equal to 0. So our point in the blood sphere will be here. This is going to be 0. Okay? So this is correct, I guess. Unless I'm really unlucky that I started with the only state that it's going to work both ways, but I don't think so. It's clear for everyone what I just did. You're going to see, if you continue working with quantum information, you're going to see this picture for the rest of your lives many, many times. So it is important that it's clear, okay? And now we try to do the same for the other vectors. We figure out what are the angles for the corresponding state, and then we compute the coordinates of the point representing that state. That's that state. Is it clear for everyone? Okay. So I'll just do one more, the plus, and the rest of them you can do for homework if you want to. It's really similar. So this is 1 square root of 2, 0, 1. And if we remember, our state should be written like this. So we need that cosinus of theta over 2 be equal to 1/2, 1 over square root of 2. This has to be 1 over square root of 2 as well. This implies that theta has to be pi. And then what we have inside here is pi over 2, which is going to give 45 degrees and gives us this 1 over square root of 2. And we need that e to the e phi be equal to 1. And there's no phase here, no sign or another complex number. So this and this here means that phi needs to be 0. So going back now to the um, coordinates of the points. So we will have here with these two angles, x equal to cosinus of 0, sinus of theta. There's something wrong.
It should be pi over 2, no?
Yes, thank you. Because I need 45 and 45 is pi over 4. Thank you. Now it makes sense. Pi over 2 sinus of 0, sinus of pi over 2, and z is equal to cosinus of pi over 2. And this is going to give us 1, 0, 0. And if we draw our sphere again, this vector will be here. And if you notice, because here we go from remembering that psi is theta over 2, 0, plus minus g theta over 2, 1. Here in the vector in C2, we are using theta over 2, while here in R3, we're just using theta. So whenever I have a 90-degree angle in C2, I have a 180 angle in R3 because I'm multiplying the angle by 2. So you will see that orthogonal vectors in C2 are going to be mapped to opposite points, antipodal points on the sphere. So 0 is here as we computed. 1 will be down here, 180 degrees. And according to this, it's a bit different from my drawing over there. Let me change it so we are going to have the same. So the x-axis will be here, and our plus vector will be here, just so they are equal. This is going to be plus, and minus is going to be in the other side of the sphere. And if you look at the other vectors that are also important for 1 qubit, I like to use this symbol. I never exactly know which one is which. I just draw them randomly here. It's just like a round arrow. The eigenvectors of the sigma y Pauli matrix. They are going to be the antipodal vectors aligned in the y-axis. So this is homework for you. Okay. This coordinates here, this pointing R3 is called the blob vector associated to that state. So we are doing a one-to-one correspondence between our state psi and this vector. It's called the blob vector. And sometimes we just use the blob vector to represent our state instead of using a vector in situ. We just use this point in the blob sphere. And another homework for you, and that is really interesting. We can do it in another time if you have any difficulties, but there's no, it's just a calculation here. Here I'm using a simple notation, but what I'm calling X is what generally in physics we call sigma X, is this simple matrix here. Y is this. I never remember where is the minus sign. So another homework, check the minus sign. It makes difference, okay? So if I'm wrong here, correct me. And it's also represented as sigma Y and Z. So it might be the case that this minus sign is in the other eye, okay? And the mean value of an operator is this sandwich here, which will be the vector psi, the matrix here, and the other vector here. So we have to do this calculation for each of them, and y the same. So you will notice that if you get this state with these entries, if you use these three matrices and compute these matrix products here, you will get exactly the coordinates of the blob vector, okay? You might have to, you have to do the computations. You might have to use some trigonometric relations. So it might be a bit boring, but it's not difficult, and it's something that we use a lot, okay? So again, this is something that you're going to see many, many times. Okay, questions? Okay, now I want to remind you of something that we talked about a little bit last Monday, last class, last lecture. And it's really simple. You already did it many times on your quantum physics undergrad, grad course, or studying for a WEF or anything. So this is something that you've done many, many times. And here I'm going to do it for the most simple system, that is a qubit. So this is a piece of cake for you already. but I wanted to be sure that everyone is on the same page. Many of you already know, I know you work with quantum physics for a long time, but there are people here that are not actually working on the field. So I just wanted everyone to be on the same page. So I will redo this simple calculation, but it's the soul of the protocol of the quantum cryptography protocol that we're going to use later. So it's easy, but it's super important. So we're doing it again. So again, I want to focus on these four vectors, 0, 1, and plus, minus. And the interesting thing is, as we computed last class, they are the eigen vectors of z, 0 and 1, and x, plus and minus. So if we look at the uh, operator z, we one important thing here. Sometimes when we're studying quantum physics, they already define the sigma x and sigma y with an h bar here, multiplying these matrices. And again, this is important when you're dealing with a specific physical system, but it's not that important here because we just need to differentiate between the two outcomes. Doesn't matter what is the label that you use for each outcome, okay? So it might be that bit of difference depending on how you saw it on your quantum physics course. Okay, so I know that this operator has two eigenvectors, lambda 1 equal to 1, with eigenvector 0. And lambda 2 equal to -1 with eigenvector 1. And because of that, I know if I have a state like this, and if I apply measurement z to psi, I in general will have two possible outcomes. So I have outcome plus 1 with probability p1 equal to psi. This is a small p and this is a big P. P1, P1, in which this P1 is the projector 0, 0. This is the same thing as psi 0, 0 psi. These numbers are one the conjugate of the other, so this is the same thing as modulus of 0 psi squared. The inner product of the vector with 0, because this is an orthonormal basis, is just the coefficient in front of alpha, in front of 0. So this is modulus of alpha squared. So there are two ways in which you can compute the probabilities. You can use the projectors, or you can write the vector in the right basis, in the bases made of eigenvectors of your operator and look at the coefficients. Sometimes one is easier, sometimes the other is easier, okay? Okay. And you have outcome -1. Oh, before that. The final state of the system after the measurement is P2 equal to psi P2 psi. P2 is 1, 1. And the same thing here. Psi 1, 1 psi. Which is modulus of 1 psi squared, which is modulus of beta squared. Okay? And no, I'm crazy. I was going to do that, and I remember I had to do something else before that, and then I did the same thing again. So the final state, psi f, given that outcome 0 was obtained, or outcome 1, is P1 psi over the modulus of P1 psi, which it's only going to give you trouble to compute when there are degeneracies in your matrix. If there are no degeneracies, this will not depend on the initial state. It's just going to be, in this case, 0, always. Okay? If there are degeneracies, then this computation is not that simple, but that's not the case in this class. Maybe next class. Okay, but we have outcome -1 with probability. This one that I already computed because I was crazy. Which is just this coefficient, modulus of this coefficient squared, and the final state is psi f, given that outcome -1 was obtained, P2 psi over the norm of this guy, which is always going to be equal to 1. Might be that depending on the vector you started with, you have like a global phase here, which we already know doesn't make any difference when we talk about quantum states, okay? Okay, simple so far? Okay, now we do the same thing for x. So x is this guy here. We already talked about it last class. It has two eigenvalues, lambda1 equal to 1 with eigenvalue with eigenvector plus, and lambda2 equals to -1 with eigenvector minus. And now we have the same thing. Now, if your vector is written in terms of plus and minus, this becomes easy again. So you have probability of outcome 1 equal to gamma squared. The final state, it's always going to be plus. And the probability of the second outcome is the delta squared. And the final state is minus, okay? This is a case where you might not like write, generally the vector is written in the canonical basis, 0 and 1. And to compute these probabilities is easier to use the projectors than to rewrite the vectors in terms of this basis. It's just computation. You can ask the computer to do it for you. You don't need to waste your time with these things. But you'll get the idea here, okay? So important for us now is what happens to these four vectors. 0 written in the plus minus basis. Let me just I will try to understand what happens when I apply the measurement z and x to these four measurement, to these four states. So 0 written in the plus minus basis is equal to this, and 1 is equal to this. Plus is equal to and minus. So if I apply the measurement x to 0, I have P1 equal to P2 equal to 1/2. And here the same. And if I have measurement z, in this state, I have P1 equal to 1, P2 equal to 0, and here the opposite. Is it clear for everyone? So 0 is an eigenvector of z, so I have a definite answer. And 0 has 1 over square root of 2 coefficients for the eigenvectors of x, which will give me 1/2 probability for each outcome. And here with plus and minus, we'll have the opposite. So if I measure x, I'll have P1 equal to 1, P2 equal to 0. Here the opposite. And if I measure z, I'll have P1 equal to P2 equal to 1/2. And here the same thing. Okay? Very simple, but very important. This is the soul of the cryptography protocol we're gonna see in a minute. Okay? Questions so far?